Cryptography Fundamental 6, Chinese Remainder Theorem, CTR. And so a large army met. The general asked the collected troops to range themselves into groups of 50. He counts there are 4 troops left without a group. He then asks for the groups of 60, and there are 14 left. And finally, he asks for groups of 70, and there are 24 left. The general stands up and tells the army that they are 201,554 strong. So how did the general do it? Well, he took army mod 50 to give 4, army mod 60 to give 14, and army mod 70 to give 24. From this, he used CRT to compute the result of 201,554. The Chinese remainder theorem was first published by the Chinese mathematician Sun Tzu. It determines a number x so that when divided by some given dividers leaves given remainders. As public key encryption typically involves this type of operation, CRT is well set up to crack encrypted messages. So what value of x will x equal in the following? X mod 3 equals 2, x mod 5 equals 3, and x mod 7 equals 2. The answer is 23, as 23 divided by 3 gives 21 remainder 2, 23 divided by 5 gives 4 remainder 3, and 23 divided by 7 gives 3 remainder 2. CRT and RSA. In RSA, we determine the cipher equal to the message to the power of E mod M. If we capture enough encrypted messages with the same E value and with a different modulus value N, we can crack the message using CRT. For example, if we have an E value of 3, we just need to capture 3 cipher messages to be able to recover the message. In the following case, we use P1 and Q1 to generate a modulus N1, P2 and Q2 to generate a modulus N2, and N3 is made up of P3 and Q3. For this, we have a message of 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, and we create 3 sets of prime numbers. When we run it, we get a number of ciphers, 3 ciphers, and we have 3 modulus values and the same N value. When we complete this, we get the m to the power of E mod of 3 values. Well, we can then solve with CRT. This gives a value of m to the power of E. Then we can use an inverse log function, or we can use the result to the power of 1 divided by 3, or to use the n root of 3 for our result. So is CRT good sometimes? Well, in RSA, obviously we can crack messages with CRT, but we can also use it to simplify the decryption process. We will cover this in more detail when we look at RSA encryption, but for now, all we need to say is that RSA generates additional values for its keys known as DQ, DP, and inverse Q, and which use CRT to speed up decryption. But there are many other attacks that use CRT, and it is one of the most widely used cracking techniques for cryptanalysis. Wiener Schindler defined a timing attack on RSA, and which involves a factorization of RSA, the RSA modulus, if CRT is used. The work goes back to 1996, and when Arjun Lenstra defined an attack against an optimization called the CRT. If a fault was generated in calculating a signature using CRT optimization, the attacker could recover the associated private key from the signature. This is known as a RSA CRT key leak. Many systems have been immune from this type of attack as RSA did not use, as TLS did not use the RSA signature. Unfortunately, the forward security option in TLS is now recommended, and this has reintroduced the problem. Researchers at Red Hat 2 also found that websites which were not hardened against this type of attack had quite a few RSA CTR key leaks. They found that the private key of the website could be leaked to an intruder who can then decode all the encrypted communications with the site and also impersonate it. So how do we protect against this type of attack? The first is to make sure that the value of E always exceeds the copies of the messages that can be copied. For this, E is typically 65,537, which makes it much more difficult to crack. Along with this, we can pad the message with random bits, and this is what typically happens with RSA. Okay, thank you.